In the last lecture, I had described two different types of collisions. One type of collision where the energy is absolutely not conserved, in particular, two objects colliding, sticking together. And when they do, the maximum amount of kinetic energy is lost. And it's lost because of deformation of the objects and the action of non-conservative forces during the collision. I don't know the nature of those forces in the collision, but I do realize that they're non-conservative. And so thermal energy is produced, or sound, or light, or whatever, and energy escapes. So energy is not conserved in an inelastic collision. But there are some cases, I made the claim, where it's close enough that the materials involved or the action of the forces are very nearly elastic, so that when the collision takes place, there's not much energy is lost. And so it becomes possible for me to use the law of conservation of energy and the law of conservation of momentum together to solve more sophisticated problems that I otherwise would not. Because consider, if I write the law of conservation of momentum, I'm only allowing myself to have one unknown. If there's one unknown quantity, I have one equation, and then I can solve. But if there are two quantities that are unknown when I try to apply the law of conservation of momentum, then I get into trouble because I don't have enough information to solve. So what I want to do now is to show you the best example that I have for, or I guess I should say the most important example that I have, for a collision where I'm going to make the assumption that the collision is elastic. A collision where I'm going to make the assumption that the energy is conserved, and I'll see what the result is. A very interesting thing about this example that I can solve. Very often when I do physics, I say, let me do the most general thing that I possibly can, because if I get the general result, then I can go around and use that general result in all the different applications that I find for it. Here, I'm going to do an extremely specific example, and the fun part about it is I'm going to discover at the end that this extremely simple example applies to every single example. So at first it seems very specific, but it'll turn out to be the most general way for me to do it. Consider, please, if you would, two objects, A and B, just like I did in the previous discussion. So I have object A here, and I'm going to do this naturally in the absence of any external forces, because I'm going to assert the law of conservation of momentum, and I can't do that if there are external forces acting. So if A is sitting on some side of some sort of surface as it goes along, I have to make the claim that it's frictionless or whatever, so there's no external force. And it moves along, has a mass ma, presumably, and a velocity va. And then here is object B, and here it sits, and it has a velocity vb. Now here's the very first of my specificity. I'm going to say let the velocity of b be equal to 0 meters per second. It's sitting there at rest. And in the last example I did, they both had a velocity. So he was very general. But now I'm being very specific and saying that B is at rest with a velocity of 0. And so A will most certainly collide with B. A and B are absolutely going to collide with each other because B is just sitting there waiting to be hit. When they do, there are action-reaction forces between them. Momentum is ultimately conserved. I want to find the velocity of A and B after the collision. So to do that, what I need to do is write the law of conservation of momentum. So I'll write that out quickly. Notice that I've written it as the total initial momentum, MAVA, plus MBVB, is equal to MAVA prime plus MBVB prime. The total initial momentum of the system is equal to the total final momentum. Well, let me start to flesh this out according to this assumption that I've made, that B is at rest. So the initial velocity of B is equal to 0, which means this second term on the left-hand side is equal to 0. So I'll strike that out. It's not there, making my problem simpler. I'll add an even greater simplicity to it by asserting that MA is equal to MB. I'll make a note of that here. MA is equal to MB. They are equal masses. And if you've already done a lot of problem solving, you probably think, well, that's lucky. And I don't often get that lucky when I'm solving problems. It's often more complicated. But MA being equal to MB means that all of the masses in this equation will cancel out. And so I'm left with a very, very simple relationship that the velocity of A is equal to the velocity of A after the collision plus the velocity of B after the collision. Appreciate that is a vector equation. And I'm doing it in one dimension, so the velocities are positive and negative, and that indicates the vectorness of it, but definitely a vector equation relationship among. Now you see exactly the problem that I have. If there are two things that are unknown, and in principle in this problem there are two things that are unknown, the two final velocities, VA prime and VB prime, I don't know them. And I've only got one equation, so I cannot solve. I'm stuck here. I've got one equation I cannot solve. So in order to extract myself from this difficulty, I'm going to write the law of conservation of energy. I'm going to assume that the collision is elastic. And I need to be told that, because remember, every collision there's some energy lost. So I need to be given permission. Well, I'm in charge here, so I'm going to give permission and say, we'll assume that the collision takes place such that kinetic energy is also conserved. And so I can write a sort of law of conservation of kinetic energy. There are no potential energies involved in this collision, so I'll just go ahead and write that the total initial kinetic energy, which is 1/2 MAVA squared, plus 1/2 MBVB squared, is going to be equal to the energy after collision. A little bit sloppy to write because I'm going to have to both have to write VA prime and then square it. So I've got like a double superscript on there. Just be careful how you write that so you can tell what you're looking at. 1/2 MBVB prime squared. So I have the total initial kinetic energy, 1/2 MAVA squared plus 1/2 MBVB squared, is equal to 1/2 MAVA prime squared plus 1/2 MBVB prime squared. And I'll assert here the same simplifications that I had in the first part, because since the initial velocity of B is equal to 0, that means that the initial kinetic energy of B is equal to 0. It's just sitting there. It has no energy of motion. And so, again, the second term on the left-hand side of the equation gets struck out because there's no energy there. And also, the masses are the same, because it's the same problem that I'm solving here. The masses are the same. So I can go along and strike out all the masses, and while I'm at it, I can also strike out all the 1/2s, because there's a 1/2 in every term. And so I end up, again, just as I did in the momentum case, with a very simple equation that is a relationship among these quantities. So VA squared is equal to VA prime squared plus VB prime squared. And if I had written the conservation of energy on its own, I would have the same problem. Here, I have the conservation of momentum, my conservation of momentum equation, where there is just one equation, in principle two unknowns. But by writing the conservation of energy down here, I also have one equation with two unknowns. And now I have two equations with the two same unknowns, the velocities after collision. So what I have to do in order to work this out and figure out what the velocities are is to do a little simultaneous solution, plugging one into the other, which is going to be a little bit of bother algebraically, but I have decent skills at that. So I have to decide what I want to do. What I think the best approach to do here is, you see how in my conservation of energy equation, on the left-hand side I have VA squared, and in the momentum equation I have simply VA. So I think my best course of action would be to take my conservation of momentum equation and square it, so that I could set it equal to the conservation of energy equation. I'll simply see what I get from that. So squaring this is going to be, or I can write that VA squared is going to be equal to the square of these terms. Well, I'm going to have to FOIL this. So it's going to be VA prime squared plus 2 VA prime VB prime plus VB prime squared. That's what I get when I square my momentum equation on both sides. Well, that naturally has to be equal to, or according to me, it has to be equal to the right-hand side of my energy equation. That is VA prime squared plus VB prime squared. VB prime squared. And we see that a rather lovely thing happens. I have a VA prime squared here on the right-hand side, and I have one on the left-hand side as well. And so I can subtract VA prime squared from both sides of the equation. I'm subtracting it from both sides of the equation. I also have a VB prime squared here on the right-hand side and a VB prime squared here on the left-hand side, so I'm subtracting, not canceling, but subtracting. And so things have really pared down to a rather absurd little statement that 2 times VA prime VB prime is equal to 0, which is a little alarming result. Rather simple, rather obvious, and in fact, I can divide the 2 over to the right-hand side, and it says that the product of VA prime and VB prime must be equal to 0. Now, if I look at this as purely a mathematical issue, I'm in trouble, because that can be equal to 0 if VA prime or VB prime is equal to 0. So, you know, there's a little subtlety here, a fun little subtlety, that we talk about the difference between mathematics and physics. According to the mathematics of this, VA prime or VB prime could be equal to 0, but according to nature, that is physically impossible. I can assert, because of the nature of the thing, that it is impossible for the velocity of B to be 0 after the collision. It cannot be, because B is sitting there minding its own business, and it is contacted from behind by A. It collides with it. A therefore exerts a force on B in the positive direction. It will have an acceleration in proportion to its mass in the positive direction. It must obtain some velocity. After the collision, it cannot be equal to zero. A can and must in order to satisfy this equation. So in order that the conservation of momentum and the conservation of energy be satisfied, I realize from this, like the conclusion that I draw, therefore, 3 dots, therefore, is that VA prime must be equal to zero. That VA prime must be equal to zero. Well, if VA prime is equal to zero, my conservation of momentum equation gives me another conclusion. I'll draw another arrow here, making things look a little complicated. Taking VA prime is equal to zero and going back to my conservation of momentum equation, I realize a fundamental thing. This equation with VA prime equals to zero means that VB prime, after the collision, the velocity of B after the collision must be equal to the velocity that A had before the collision. The 2 is irrelevant. I could divide it the other side and make it zero. Now, it's a remarkable result. It's a remarkable result because it says when 2 objects of equal mass collide elastically, the first stops and the other one moves on with the same velocity. They simply exchange velocities. It smacks of a law of conservation of velocity, but we know that that's not true. It's conservation of momentum that is what's happening. It's just coincidentally that the masses are equal. When 2 objects of equal mass collide elastically, the first stops and the other one goes on. They just exchange velocity.
So like it's cradle?
No, stops. Now, to that point, Blake, anybody who's really familiar with playing billiards knows that the cue ball on the billiard table does not have the same mass as all the other balls. This adds a little bit of jeopardy to billiards because if I smack a cue ball into any of the other balls, the cue ball follows a little bit, as you just implied. Well, they don't have the same mass.
You said that it'll take on the zero velocity.
Yes.
A on B's velocity, not just zero.
This is zero. That is an excellent point, and I'm going to come to that in a moment. Because Sarah's a little bit concerned. That's why she's asking the follow-up question. Is that this situation is not the one that's going to be on the test. Because that doesn't have, come on. They're the same mass and one's at rest. You know, that's the luckiest problem that you can have. And now you know that the answer to that question is easy. So when you're wandering around and you see one of the other physics students in the building and they're like, oh, I don't know, what would the velocity afterwards be? And you'd be like, that's 5 meters. Oh, you're so smart. Well, that's the easiest thing. We see, it may be like, well, this wasn't worth doing because you see what you've done is you've created a situation where I can solve that one problem, but I can't solve any of the others. The fun thing about this is I have solved every elastic collision problem by doing this. Here's why. First, consider, what if B were more massive than A? Or A were more massive than B? You see, I've made the assumption here that the masses are equal, but what if they're not? Well, here's the thing. If I might make the velocity of A twice the velocity you described, if I make the, I'm sorry, did I say velocity? If I make the mass of A twice the mass of B, now I've got a situation where I have a collision where the masses aren't equal. I can fix that because momentum is mass times velocity. So all I have to do is pretend that it's not the mass of A that I doubled, but its velocity. Now they have the same mass, and A just has double the velocity. And so how do they collide? Where B will pick up the enhanced velocity. So all I have to do is think about it differently. Instead of thinking of A as being more massive, I just think of it as being the same mass with more velocity because momentum is mass times velocity. You multiply it on, but yeah, I don't have to. I don't have to because I'm done. I've already established that when 2 objects with equal masses collide, that's what happens always. So I don't have to reestablish that. All I have to do is say, oh, now this one has twice the mass. No, it doesn't. Twice the velocity, which is twice the momentum, All I have to do is give it twice the momentum. I don't have to give it twice the mass. Off it goes. Now, Sarah's point is, wait a second, what if they don't have the same velocity? No, actually, to establish it a little bit more firmly. What if the velocity of B is not zero? Now you've got a problem, right? I get it, the masses, you fix the mass problem. But what if the velocity of B is not zero? Here's the fun thing. This is next level stuff. You ready? This is the more challenging physics. Ready? I can make it zero. I can force it to be zero by solving the problem in a coordinate system that moves along with the velocity of B. If I move along with the velocity of B, then B's not moving in that reference frame. And what happens in the collision? I can choose. You know, it's funny, Blake, at the beginning of physics, I go on, I sound like a lunatic. The choice of coordinate system is arbitrary, and some coordinate systems are better than others. And people are like, why do you keep stressing that? I choose the coordinate system, and I choose one that goes along with a velocity v. I cannot choose a coordinate system that's accelerating, because then that messes up my Newton's second law, right? You can't do that. Well, I mean, you can, but you have to be prepared for the fact that it messes up. You're going to get fictitious forces. But I can choose a coordinate system that goes along with a velocity v. So all I have to do is choose my coordinate system so that the velocity of my coordinate system is vb. But then that messes up A's velocity. It's a relative velocity thing. All I have to do is take VA and minus VB, and that's the new velocity of VA, and I have solved every elastic collision problem right there. Yeah.
VA is gonna halt. Isn't that just it taking on VB's velocity?
I'm sorry, Sarah, say again. It's going to be, no, it'll do what's described here. VA will stop.
Yeah, but if you say that it's initially it's
Yes.
per second and then VA
Right. So here's what you have to do. This is the language of it. So I look at the problem and B has an initial velocity. I'm like, I learned how to fix that. I just have to subtract B's velocity away from it, all the velocities. I'm going to subtract B's velocity away from all the velocities. Now I have transformed, this is the language. I have transformed into the moving reference frame, into B's reference frame. I've transformed into, like I'm riding along on B. And if I'm riding on B, its velocity, look, I'm standing on it, its velocity is 0. So I've transformed in. Once I do the math and I get my answer, once I bang, bang, done, I have to transform back again by adding B's velocity to all the velocities in the problem. So you transform into a moving coordinate system and then you transform out again. You transform in by subtracting. You transform out by adding.
So isn't that if you go in to once you transform in, VB is 0. When you transform out, isn't VA prime going to be what V was?
But VB, oh, you mean VB before you transformed in?
Yeah.
Not necessarily.
Yeah, and once you transform out, isn't VB going to be equal to VA prime? Because you're transforming in by the same amount.
Oh, yes, because I'm going to add VB to 0 and get VB. Yes.
So they're
Yes.
velocity. Okay.
Yeah. Which means that elastic collisions are much simpler than they seem, right? And I can solve any elastic collision by simply transforming coordinates and making the masses proportion and then assuming that A stops and B takes that velocity. That is pretty remarkable. Put your checkbook away, there's more. In a future lecture, I have even a better way of doing this. A way that will make it possible for you to find some poor student who's suffering through conservation of momentum problems and look at the problem and solve it in your head inside of 30 seconds, depending on how your arithmetic skill is. All right? It's going to be pretty exciting. But that's for the future. What I want to do now is another sort of formality. It's an exercise of algebra, I suppose, a little bit. But I want to be able to address the issue of the fact that this is a little bit of a fantasy because energy is not perfectly conserved. And Blake, as you said, won't it follow a little bit? Won't A follow along a little bit? And that's your life experience that's saying that. And when you first said that, I responded by saying, well, no, because the masses are equal. But even if the masses are equal, A may follow a bit because the energy is not absolutely conserved. The energy is not absolutely conserved. So I don't expect this is idealized behavior. So what happens in the non-idealized case? I'm going to do a little bit of algebra again. And so I'm going to start with my conservation of momentum, MA VA plus MB VB is equal to MA VA prime plus MB VB prime. That's a law of conservation of momentum. And now I am not going to tinker with it in such a way that I have equal masses or equal velocities. I'm not going to set anything equal to 0. I'm going for an absolutely general result. And then over here I'll write my conservation of kinetic energy again, 1/2 MAVA squared plus 1/2 MBVB squared is equal to 1/2 MAVA prime square plus 1/2 MBVB prime squared. I have to be careful. I'm letting my handwriting get a little bit lazy. Now, these equations are written for a specific utility of initial equal to final. Initial equal to final. What I'm going to do is change them around so I write them in terms of A on one side and B on the other. I'm going to swap this equation around so it's the A terms on one side and the B terms on the other. Currently, it's initial is equal to final. I want it to be A is equal to B. And that's really easy to do. I simply have to move my terms around such that MAVA minus MAVA prime is equal to, and on this side, MBVB prime, which was already there on the right-hand side, minus MBVB. And obviously now I have, on the left-hand side, I have the mass MA in both terms, and on the other side I have the mass MB. So just for fun, I'm going to write this as MA times the quantity VA minus VA prime, it's nice and compact that way, is equal to MB times the quantity VB prime minus VB. I get that relationship there. And so now I'm done working on that for a moment. I'm going to take a step to the right and work on my kinetic energy equation. I'm going to do exactly the same thing. Remember, the masses are not equal to each other, but I can cancel the 1/2. So in the next step that I have, the 1/2 are going to disappear. And I'll do the same thing as make everything on the left-hand side A. And so I have MAVA squared minus MAVA prime squared is equal to MBVB prime squared minus MBVB squared. A's on one side, B's on the other. And again, the same situation has happened with my momentum equation. I'm doing this lovely little parallel thing here, where the masses can be factored out on both sides. That's a perfectly fine thing to do. And I realize that this little derivation that I'm doing, which is quite the exercise, is just a whole boatload of algebra. And I wish I could tell you that the payoff is going to be something amazing. But it's just going to be kind of, It's just going to be kind of, So then I didn't label my MA there. Hang on. MA. All right, super. So now I'm going to leave my momentum B, and I'm going to bring this equation here, my energy equation, I'm going to bring that to center focus. And I'm going to notice that I can expand this term, VA squared minus VA prime squared. I can expand that term because what it is MA times VA squared minus VA prime squared times VA squared plus VA prime squared. If that's not immediately apparent to you, you can just FOIL that in your head and see that it's equal to the left-hand side of the equation that appears above. Oh, no, I'm sorry. Pardon me. There should be no squares. Let me try again. I'll give it another try. What's that? Because I'm going to go from there down. I think I have an aesthetic thing that I'm doing. It'll work. I don't know. Not if I can't do algebra properly. I'm going to be in trouble. So let me make it VA minus VA prime times the quantity VA plus V prime, or VA prime, right? Like that. And you can see by foiling that that is equal to the left-hand side of the previous equation. And so that is equal to, on the right-hand side, I would do the same thing. MB times the quantity VB prime minus VB times the quantity VB prime plus VB on that side. All right, so I just sort of expanded those squared terms, and what I see immediately, a lovely thing happens. You say, look, according to the law of conservation of momentum, MAVA minus VA prime is equal to MBVB prime, and here they are. MAVA minus VA prime appears right there on the left-hand side of my energy equation. On the right-hand side of the energy equation, there appears that. Those two terms are equal to each other. And so, what I get from that is a much more compact piece of physics here, which VA plus VA prime is equal to VB prime minus plus VB. Now, this equation is still in the form A's on the left, B's on the right. So I'm going to go ahead and rearrange it again so that I have initial on the left and final on the right. And so what I have is VA minus VA prime is equal to VB prime minus VB. That is an equation that some of you may already be familiar with. It was an equation that is taught in lower level physics classes in order to give leverage to solving elastic collisions. But I'm going to take it a step further just to round out my discussion. Did I? No. Yeah. Oh, no, my goodness gracious. No, seriously, that's worth asking. You know what it is? I think maybe, and I hate to say this because I feel like maybe I'm just bored. Because I wasn't even thinking about what I was doing there, obviously. How do you like that? Yeah, that would make a lot more sense. I appreciate it. It's great when I do that and I turn around and just everybody in the audience looks horrified. Which, if you think about it, that's a really great sign for you guys as a physics class that you know it when you see it. That's really good. If I turned around and you were all smiling contently, that would be alarming. Once, like later on today when I figured out I'd made that mistake, and then we'd have to sit down and have a talk about how you didn't see it. So once again, I appreciate you watching. So this is an equation that's familiar to some of you who've done some conservation of momentum before, perhaps. But I'm going to take a strange step with this, and I'm going to divide the VB prime minus VA prime to the other side of the equation. That's odd. So that it's VA minus VB. Now everybody's watching me very closely, so I'm feeling self-conscious, so I'm going to try extra hard to be right. What's that equal to? Well, of course, it's equal to 1. It's equal to 1 because I have made the assumption that energy is conserved. But if the energy is conserved, it is not equal to 1. If the energy is not conserved, then this is not equal to 1, but is in fact equal to, and I thought about this and thought about it. There's got to be a symbol for it, and I feel like the symbol is lowercase e, but that can't be. So I'm going to call it epsilon. And it has a name in physics. It's called the coefficient of restitution. Restitution. It's equal to 1 when energy is conserved. But the coefficient of restitution gives me a number that describes the extent to which the energy is not conserved. Notice, it is not the fraction of the energy. The coefficient of restitution is not a fraction of the energy. It is the ratio of the relative velocities. Because when I subtract the initial velocities, what I get from subtracting the initial velocities is the rate at which the objects are approaching each other. When I subtract the initial velocities, I get the rate at which they're approaching each other. When I subtract the final velocities, I get the rate at which they're receding from each other. So the ratio of the approach velocity to the receding velocity is known as the coefficient of restitution. It is a number equal to 1 when energy is conserved, and a number greater than 1 when the energy is not conserved. It is extraordinarily unlikely that any of the problems that you will be assigned or any exams that you'll do will mention the coefficient of restitution, but it's simply here as a completeness for a discussion of elastic collisions.